So today, any questions about what we did? I even put up that problem. If you looked, I did the problem, I think it was, what, 3-2.1, the conditional probability one. I put it down there. Did anybody look at, somebody asked me to do this. I forgot who it was. He's not even here who asked. But I put it up there. Did anybody here look at that?
You're talking about the problem, not the exercise.
The problem. Mm-hmm. Did you all see it or not? All right. Now, I did that, and I try to show you at length how to do all this stuff. The biggest problem, the biggest thing to remember is when you have noise plus a signal, and noise has statistics, and the signal has statistics, but the observation doesn't. If you are given the value of the signal x, then the probability of f of y is really going to be just the probability, since x is given, of y minus x. Take that argument and take that argument and use it for the f of n. Replace n with y minus x. Then you have the statistics for y given x. Y'all with me on this? So that's important. So today, any other questions about section 3-3 before I get going on this? Got a whole bunch of stuff to talk about today. Today, we're into section 3-4. In the old book, I know I've been threatening to give you new book stuff. I need to, and I will, but this is actually, I'd say, a more direct and simpler approach. The problems don't get as complicated. The other book's got some complicated stuff, and I'm trying to just get the essence of it here, okay, everybody? So this is section 3-4 in the book. And well, I'll just call it section 3-4. So the whole idea is now we're talking about something called correlation. All right? So correlation. And the first thing they do is talk about something called covariance. So remember before when you had variance of anything, right? What was the definition of variance fundamentally? It's equal to what? The expected value of, let's use x minus x bar squared, right? Technically what this is an integral of x minus x bar squared times f of x dx from minus infinity to infinity. It's just really subtracting off the mean from the value of x and then finding what that is. So it's really eliminating the effect of the mean on this. Now, when you talk about covariance, what that is the expected value of x minus x bar times y minus y bar. All right? Now, if you looked at this, it's very similar to that, right? And let me show you where this is in the book. This is on page 132 of Cooper-Macmillan, and it's equation 3-23. So covariance and variance, it makes sense. Covariance means now we're not taking a look at x minus x bar and squaring it, or times itself. It's its relation to these two things. And it's really going to be something that you're going to find out has a lot to do with something called correlation, or how much two functions agree. And we're going to get something called the correlation coefficient. But this is the covariance. Now, by definition, you can see it's really going to be equal to x minus x bar, y minus y bar, times f of x comma y, dx dy, and it's over their range of existence. Technically, you can put from minus infinity to infinity for both x and y, and these are just two functions. Now, they can be dependent or independent, statistically independent, but we don't know. Remember, last time, the only way to determine statistical dependence or independence was to see if f of x comma y was equal to f of x times f of y of y. In other words, or if we could factor them. You all remember that? You're going to see a couple other tricks here. Okay, that's covariance. That's the definition. However, something that they do oftentimes is talk about the actual correlate, or really, it's the, I think he calls it in here, this is the correlation constant, I think, but I better be absolutely, want to be clear about this. He calls it a correlation coefficient or the normalized covariance. This is important, this one. So write this down. This one you're going to know, and we're going to use it all the time. What we do is we talk about this, and this is the correlation coefficient. All right. What that is going to be the expected value of, and now you have x minus x bar over sigma x, and it's y minus y bar over sigma y. And this is shown in the book. So now what we do is eliminate both the mean, the mean's eliminated in the covariance, but now we get rid of the effect of the actual standard deviation or variance. Do you all follow me? So if we take a look at this, what does that mean? Well, this is technically going to be the expected value. Well, if you do this, there'll be a double integral of x minus x bar, y minus y bar, over sigma x sigma y, and then we do dx dy, technically from minus infinity to infinity, minus infinity to infinity. I'm going to go ahead and square out that term. So we can say that the correlation coefficient is equal to, I'm going to take the 1 over sigma x sigma y out in front. Now, when I take a look at this, and I go ahead and multiply this out, I'll leave the double integral out in front too. And then inside here, I'm going to get xy. Then I'm going to get minus x bar y minus y bar x. That's these two terms in the outer terms. And then plus x y bar f of x comma y dx dy. You all follow me? Just squared out everything, right? I've taken it and I've gone ahead with the operation, mathematical operation. When I look at this, I'm going to now go ahead and take sigma x, sigma y, and I'm going to multiply both sides of that. So I have, well, I won't actually. I'll leave it there. I have rho equals 1 over sigma x, sigma y. This is in the book. Now, what this is, the first one, xy times this f of xy, is just the expected value of xy. Do you all agree with that? So I'm going to leave it as that, because that's how the book will render it too. Now, when we have x bar, that's a constant, times y, integrated f of xy, dx dy, I'm going to get y bar there. Do you all follow me on this one? Just take a look. When I take this, and I integrate it times this, remember, x bar is a constant, take it outside, you got to do dx dy. You're going to get y bar here. So it's going to be x bar, y bar. Here you're going to get also x bar, y bar. Do you all follow me on this one? But then you add that to it. The net effect is it's going to be minus x bar, y bar here. I mean, just take a look at this. When I have x times y times f of xy. Y is a variable, right? X bar comes out in front, right? Now do the integration. When I have y, integrate of x of y dx dy. When I integrate dx, I'm going to get some value. Then I have an f of y function. Integrated with y, I get the expected value of y. Can you all go through this and make sure you're convinced of this? It works. So I get this, and you can see that now, if I want to, I can say the expected value of x times y, and you don't know if it's correlated or not, is equal to really going to be the correlation coefficient times sigma x, sigma y, and it's going to be plus x bar, y bar. And he'll have this in the book. This is equation 3-25 on page 133 if you want to take a look. Anybody have the, are you looking at the PDF, everybody?
Yes, sir.
Do you all see it? All right. Kind of circle that one. It's important. The next thing he does in the book, he says we can also do something where we normalize this and we get some information. But what I'm going to do, I'm not even going to bother with that. I'm going to go ahead and first do the example where they have f of xy equals x plus y, where y is from 0 to 1, x is from 0 to 1. We're going to go ahead and get the correlation coefficient for this. I'm simply going to apply this to what I believe is a very simple and understandable problem. Now, I'll put this back up. But if you're smart, just keep your notes open to where I define the correlation coefficient. We can go ahead and do this. Okay, so for this problem, he has the joint density function f of xy is equal to x plus y. This is in the book. And he says this is from 0 greater than x comma y, both less than 1. And it's actually in the reading. It's, yeah. And it equals 0 else. Now, this is going to be a simple one, but I want to just mention something. Before I continue, take a look at that problem. Is it statistically dependent or independent? Are x and y dependent or independent in y? Anyone? They are dependent, right? If it was x times y, they'd be independent. You all follow me? So the next thing I'm going to do is calculate the correlation coefficient. With me on this? First, I know that the correlation coefficient is equal to what? Sigma x, sigma y, right? And then it's the expected value of xy minus the mean value of x, mean value of y. Correct, class? I just put that up there. I know you're not familiar. I'm just restating. You can go ahead and craft this any way you want. You can multiply both sides by sigma x, sigma y, and then take xy to the other side. But nevertheless, we need the average value of x and the average value of y. Do you all follow me? That means we need to get fx of x, and we need to get fy of y. Do you all follow me on that? The reason for it. Right? We need that to get the average value. Do you all agree? Now, I'm saying this because I'm going to ask you to do this on the next quiz. Very likely, if I don't forget to put it on. You all with me? Or a mistake. So if you take a look at this, how do I get f of x? Let's do it right. No, let's do it over here.
Integrate.
Good. Equal what? The integral of the joint density function, right? X plus y, right? dy from where to where? You're right.
From 0 to 1.
0 to 1, exactly. What is this going to be? Well, that's going to be x, dy integrated is y from 0 to 1 is 1, plus y squared over 2 from 0 to 1 is just going to be 1/2. Do you all agree with that? Y squared over 2, right? All right, so that's f of x of x. What's f of y of y? Take a guess. And this is, of course, for x greater than 0, less than 1. It's what?
The same thing, but y.
Exactly, right. And that's from 0, greater than y, less than 1. Do you all agree? I'm honestly, the only thing I'm doing is going through every single step. I'm not assuming anything. The reason I'm doing this, I'm not trying to insult your intelligence, but oftentimes there's subtleties. You're thinking about something else at the same time you're looking at this, and your brain doesn't register what's going on. Everybody follow me there, how I got what I got and why I got it. The reason is now we want the expected value. So what's the expected value of x going to be? Or the mean of x? It's the integral of x, correct? Of x times what? F of x, right? X plus 1/2 dx from 0 to 1. Now, do you all agree with this? How many see it's going to be the same thing as the expected value of y? By arguments of symmetry. Do you all see that? All right, so what is this? Well, I integrate x squared dx. I get x cubed over 3 from 0 to 1 is 1/3. I hope I did that right? Then I have x times 1/2 and dx, that's x squared over 2, right? From 0 to 1 is just that, so it's going to be 1/3 plus 1/4, right? And that's what, 7/12, I think?
Yeah, that's correct.
All right, so that's x bar, and that is y bar. This is a good example. I'm just telling you, it's a simple one, but it goes through the steps. Now, the next thing is, if we have that, how do we get, and what I'm asking, it seems trivial, but I can tell you that people make mistakes. How do I get sigma x? Or sigma squared, it doesn't matter. Make it sigma squared. How do I get the variance of x? People. Squared, right? So now what I need to do is take an integral from 0 to 1, because that's where x exists, right? And I take x minus x bar. I'm going to just leave it like this, right? I take it and I go ahead. Actually, why don't we do it this way? I'm going to go take back a step before. I don't need to do this. What I'm going to do is say this. Because it's just the variance we're after, isn't the variance of x equal to simply the expected value of x squared minus, minus the mean value of x squared? Do you all agree with that? Remember that the expected value of x squared is the variance squared plus the mean value squared. Do you all remember that? We could prove it, but hopefully you remember that. Okay, so what I'm going to do, I've got the mean value. I'm just going to get the expected value of x squared. It'll be easier, I believe. You with me? So I come over here. All right, maybe I'll do it here. So I'm going to get the expected value of x squared, and that's going to be equal to an integral from 0 to 1 of x squared times f of x, which is right there.
X plus 1/2.
X plus 1/2 dx. And you all agree that's going to be the expected value of y squared because of arguments of symmetry? Y'all with me, class? Okay, what's this going to be? Well, that's x cubed dx, or x to the 4th over 4. From 0 to 1 is 1/4 plus 1/2. And then I have x squared dx, or x cubed over 3, right? From 0 to 1 is going to be 1/3. And what's that going to be? That's 1/4 plus 1/6. And then what is that, 10/24?
That's what I got.
And that's what? 5/12. I guess you could put it as 5/12. Do you all agree with that, class? And that is the expected value of y squared, is it? Pardon me?
Never mind.
Expected value of y squared. So now what's the standard deviation? Let me do it over here. Or I'm sorry, the variance. I'll do it right here. What is the variance going to be? Well, that's 5/2, right? That's expected value of x squared, and it's minus, what is that? 7/12, right? Squared. Y'all follow me what I'm doing? I'm simply putting in the expected value of x squared is the same thing as y squared.
It's 5/12.
Pardon me?
5/12.
5/12, my bad. 12, sorry. Forgot the one. 5/12 minus 7/12 squared. What is that? Anyone?
11/144.
Thank you. 11/144. All right? Okay. Which is sigma y squared, correct? Okay. Now, the square root of this will be sigma x and basically sigma x and sigma y are the same, right? So I come over here, and let me just, I'll do it here. And I'm going to try, I'm not trying to fly through this, but I'm trying to get to some other stuff. After I have that, I want the correlation coefficient, right? We've got sigma x, got sigma y, got these two, right? But we don't have this, do we? So how do we get that? Well, actually, we're going to get that. We're just going to go ahead and brute force it. I'm not going to try to do any tricks, but I think from arguments of symmetry you can see some stuff. So the expected value of x times y is going to be, it's got to be a double integral from 0 to 1, 0 to 1. Here I have to put x times y. Then it's going to be x plus y dx dy, because that is the f of xy. You all agree with that? Some of you can see a lot of symmetry there, by the way. So what is this going to be? Well, technically, I'll just put it this way. Double integral from 0 to 1, 0 to 1 of x squared y, and it's going to be dx dy plus double integral from 0 to 1, 0 to 1. And this is going to be y squared x dx dy. I'm going to make the argument that this is going to be the same as this through arguments of symmetry. Do you all agree with that? Yeah, if you look at this, these are dummy variables, right? If you simply take x here and make it y, and y make it x, then switch these, dy dx, it's the same thing as this, right? Those are dummy variables that get integrated out. I need to evaluate the first one. What's it going to be? So when I take a look at this first one right here, we're going to take 2 times that. I have x squared dx is x cubed over 3, right? From 0 to 1, it's going to be a third. Then I have y dy is y squared over 2, correct? So I have 1/3 times 1/2, right? Or 1/6. Do you agree with this, everyone? So this is going to be 1/6. This will also be 1/6. Add them together, you get 2/6 or 1/3. Do you all agree? So this, the expected value of xy, is 1/3, unless I goofed.
That's correct.
I mean, are you all understand why I'm doing what I'm doing? And this is a little lengthy, but the essence of this, it shows every step, everything you need to consider. Now, these integrations could get a lot more difficult, but the same technique would be used to get the end result. Finally, I come over here. They want this correlation coefficient, because that's the game. So the expected value of xy is 1/3. I'm going to just put it down here, 1/3. And it's minus x bar, y bar. Well, x bar and y bar are 7/12, so it's really minus 7/12 squared over sigma x and sigma y. Since sigma x and sigma y are the same, it's really just sigma x squared, or the variance of either of them, right? And that variance is, where the heck is it? Is 11 over 144. This I thought would be a lot less, but that's what it comes down to. Now, I suppose if you want to, you can fuss with this. Multiply everything, top and bottom, by 144 over 11 and mess with it. But what's the answer? Because I can't tell.
Negative 1 over 11.
Is that what it is? All right, minus 111. Now, anytime the correlation coefficient, hear me now, is not 0, they're dependent. You knew they were dependent by looking, all right? Now we have the level of dependency given by that correlation constant. By the way, the larger this value, the closer they are in terms of their behaviors. Go ahead. Let me try to answer that by showing you this. If I have 2 waveforms, let's say I have this waveform here, sine wave, right? Now I have another waveform. It's exactly that, only phase delayed, right? When one is, first they're correlated. You all agree with that? But there's going to be a time difference over which, and it's called tau. It's really something called a cross-correlation function that we're going to get to. Negative means one lags the other. Positive means one is ahead of the other. That's the only thing. What do they mean by ahead? Well, this is periodic. If it's non-periodic, the only thing means the one that's lagging, the event happens. I mean, it looks like the first one only at a delayed time. If it's positive, it would be a positive value. But you're going to see this when did you guys have correlation, by the way? You had convolution, right?
Yes, sir.
And in essence, what does a convolution of 2 functions tell you?
Frequency, domain, multiply.
Well, no, you're going way out in the limit. No, I mean, if you convolve 2 things, it really, whether you know it or not, tells you how much one thing is like the other. And we'll get that. Only it's a negative type of, oh boy, correlation is really how much things agree. And usually when you do correlation, if they're non-periodic, it kind of loses meaning. I mean, if it's an energy, not a power signal. If it's power, in other words, they have to have some periodicity, then it tells you how much one signal agrees with another, and we'll get to that. You'll see a lot of this in time. That comes up in a little bit, but right now I've got to get through this. I just got to show you the mechanics of actually calculating the correlation coefficient. Now I want to do some examples in the book. Well, I want to do one other thing. So I got to make something obvious to everybody here. And this is in the book. It gets a little crazy. And the first exercise in this section is actually got wrong answers. So before I get there, let me just say this. if I'm looking at the expected value of quantity x minus x bar, y minus y bar, I mean, that is the covariance, right? By definition. Now go ahead and expand that. That's the expected value of, here I'm going to get x squared. I'm sorry. Actually, let me do something here. I want to see in the book where this, let me do it this way. Sorry. I'm not going to do covariance on this one. I'm going to show you one other aspect of, or use for the correlation coefficient. I'm sorry, I have to backtrack a little here. If you say you have z, a new variable, is equal to y plus x, or x plus y, and you want statistics about z squared, which would be y plus x squared. This is going to come up a lot. You all with me? So if you wanted the expected value of z squared, the book doesn't show this as z squared, but I want you to think of it as z squared. The expected value of z squared would be equal to the mean value of z squared plus the standard deviation of z squared. You all follow me? It would be, if you think about this, think of this as just a single variable of z. I shouldn't put z squared. And this is actually going to be the mean value of z squared. I said that wrong. I'm sorry about that. You all with me, class? You know, the expected value of x squared is the mean value of x squared plus the standard deviation of x squared, right? Or, I'm sorry, the variance of x squared, right? Okay, now with that in mind, now we're going to go and say this is the same thing as the expected value of quantity x, and he'll have plus or minus y squared here. With me? This is in the book. It's probably sequential in the next part of that next page or so. So that's the expected value of, here it's going to be x squared. That's the first. Then I'm going to take y squared out in front here. I'm doing it for a reason. You all see that there would be minus y would give you it would be y squared. You all follow me? Plus y squared. And then you're going to get what? It's going to be minus 2x bar, or 2x, sorry. Minus 2x y. And that's what you get. Do you agree with this? I'm just expanding. Everybody, keep watching. And it should be actually plus or minus that. I'm sorry about that. It should be plus or minus this. If this is a plus, this is a plus. If this is a minus, that is a minus. Do you agree? Everyone? Now, go ahead and do this. So I have the expected value of x squared plus the expected value of y squared. And it's going to be plus or minus 2 times the expected value of x times y. And here I'm just expanding that, right? There's no tricks here. All right. So what is the expected value of x squared? It's x bar squared plus sigma x squared, right? What's the expected value of y squared? It's y bar squared plus sigma of y squared, or the variance, right? So I'm going to do that for this and this. And this is going to be x squared plus, or I should say x bar squared plus sigma x squared plus y bar squared plus sigma y squared. Doesn't matter the order. And now that's these two. And then I get plus or minus the expected value of x, y. Y'all agree with this? Now this is in the book. I'll tell you, it's on page. He doesn't do it the way I'm doing it. He does this normalization stuff, but this is on page 135. I'm doing it this way so you see the whole 9 yards. All right? Now, I get down to here. What is this? Well, remember what the correlation coefficient was. Expected value of x times y minus x bar y bar over sigma x sigma y, right? So the expected value of xy is really equal to, if you look at this, is going to be rho, the correlation coefficient, sigma x sigma y, and it's going to be plus x bar y bar. Do you all agree with that, class? Okay. So now what I'm going to do is simply replace this with plus or minus, and this is going to be, there was a 2 there, so it's going to be 2. Let me put the 2 inside. So it's 2 rho, and 2 rho sigma x sigma y, and it's going to be plus 2 x bar y bar. And he'll have that. He actually doesn't have it the way I have it. I'm going to do something in a second. But you all follow me on this? Now, I suppose I could expand it a little. Yeah, why don't I do this? I'll go ahead and leave this plus or minus here, and I'll leave this plus or minus here. And now we're going to take a look at something. Now, if you just look here, I have x bar squared, y bar squared, sigma x squared, sigma y squared. And I have this stuff that has to do with the correlation coefficient, right? Now, I started out back here and saying that is the expected value of z squared. You all with me? Now, take a look at this. When I have this and this, sigma z over here, right, is really sigma squared of x plus y, correct? So I'm going to put it over here. Then I come over here, and I see sigma z squared. I see z bar squared. Well, what is z bar? That's the mean value of x plus y, or it's the expected value of x plus y. Follow me on this? That would be the expected value of z, because z is x plus y. What is that going to be? It's simply the expected value of x plus the expected value of y, correct? Right? Now, that has to be squared here. So it's going to be whatever x is plus whatever y is squared. You're going to see this in 1 second. You with me? Now I'm going to go ahead and I'm going to square these things out. So if I do this, I'm just going to square these things. So I'm going to get x bar squared, y bar squared plus 2x bar, y bar squared. And technically this should be plus or minus. And this should be plus or minus here. So it's plus minus there. And that means this becomes sigma of x plus y squared plus, and then you're going to get x bar squared plus y bar squared, and it's going to be plus or minus 2x bar y bar. Now, the reason I did it this way, he doesn't do it in the book, but you're going to see something. My goal is to get this. I want that. That's the variance of x plus y. And technically, I should put x plus or minus, okay? Now, take a look over here. Really what I'm going to do is erase this middle part so you can see this a little better. This is what I'm after, right? And I've got these right over here. Technically, this is going to be plus or minus this stuff. Or actually, it's plus the x squared stuff. And it's plus or minus those product terms. Now look over here on this side. Here, I have x bar. You see there's x bar squared over there? Here's x bar squared. There's x bar. You with me, class? Forget all this stuff over here now. So if you look at that, can't I cancel those, the x bar squared? They go away. What about the y bar squareds? See them? This is x bar squared goes away. Now y bar squared goes away right here, right? Now we have plus or minus 2x bar y bar. Plus or minus 2x bar y bar. that goes away. And now you get this right here. And this is what he has in his book, but that's how he gets it. So sigma of quantity x plus y squared is equal to sigma x squared plus sigma y squared. And then it's going to be plus or minus, this is plus or minus, 2 times rho sigma x sigma y. And he has that in the book, page 3-28. You're right. I'm sorry, page 135, equation 3-20. Y'all with me? How many see this right here? It's a lot. I know this is new. I wanted to go through that entire proof for one reason. In the book, if you read through and try to do it, you're going to get a little lost with some of the normalization, in my opinion. At least when I start looking at that, I'm there, why not just brute force it and you'll see everything. You don't need to play around with that. So the next thing I'm going to do is exercise 3-4.1. But I want to tell you the answers I believe are wrong. Let's see if I'm right or wrong. Okay, I'm going to leave that up there. And now, 3-4.1. You're all mic'd up. Are you ready?
And this is the exercise, not the
Yeah,
problem.
it's exercise. Sorry.
On page 135.
Yeah, go ahead. Oh, wait 1 second. I'm trying to eliminate anything that, any of these markers that die on me. I'll get 1 lecture out of most. Go ahead.
2 random variables have means of 1 and variances of 1 and 4, respectively.
All right, hold it. Y equal 1 and a variance of,
1 and 4,
so sigma x is 1, sigma y squared equal 4. Go ahead.
and that's respectively. And then their correlation coefficient is 0.5.
0.5. Pause it. Go ahead.
Part A is find the variance of their sum.
All right. That right here is the variance of their sum with a plus. You follow me, class? That's the variance. Their sum would be x plus y. Do you all follow me? Can you all see this? So that's the variance of their sum. So this is part A. So I'm going to put sigma of x plus y squared is equal to sigma x squared plus sigma y squared plus, because it's a sum, 2 times rho times sigma x sigma y. Now help me out here. That means this sigma of x plus y squared. Sigma x is 1, according to what you told me. Sigma y is 4, right? Plus 2, correlation coefficient is 1/2, isn't it? You said it was 0.5. And what's sigma x? Well, it's 1. What's sigma y? It's the square root of 4, right? 2, right? So it's 2. What's this going to be? Well, that's 5. That's 2 is 7, right? Now, you're going to look at the answers. There is no 7.
Yes, 19.
All right, now, no, the first answer does not mean it is the first part. They mix them up with the answers in the exercise, just so you know. All right, but you see the lowest one there is 10, right? Now, what if by chance, instead of a 2, you go ahead and you put 4 there? What do you get? I mean, what I'm saying is, what he did is probably what a lot of people do, is made a mistake and put the variance either here or here, rather than the standard deviation of one of them. That's what I think happened. I was playing around with this. You all with me? It could have been either. Anyway, he's wrong. That's exactly right. Do you all follow me on this? You're going to see in the next exercise we'll get it right. What's the next part? They're all wrong, by the way.
Find the mean square value of their sum.
All right. Now, so now what he wants is this. Mean squared means it's got to be squared. He wants the expected value of a sum. That's x plus y squared. With me? Now, what do you know? Really, I know if I'm trying to say this, if we let z be equal to x plus y, right? Then the expected value of z squared would be equal to this squared plus sigma of z squared. You all follow me on this? All right. Well, since z is x plus y, the mean value is just x bar plus y bar squared, right? And squaring it. So this is going to be equal to x bar plus y bar squared plus, Didn't we just get this over here? Right? The first part, we got the variance of their sum. Didn't we, class? Y'all see that? So now I come over here, it's 7, right? So it's going to be plus 7. Now, follow me on this. X bar and Y bar, according to what you told me, have means of 1. Right? I mean, that's what it says. So what's this going to be? That's going to be equal to 2 squared plus 7. That's 4 plus 7, or 11. Do you all see that? He's going to be off by, I think, 3 on all these. Maybe more than that. It's 3 squared on that one. 17, I think, is what your value should be. Or 19. I forgot what it is. With me, class? But that's how you get the sum. What about the difference? Do you all agree with this? What's the difference going to be? Well, this would be x minus y squared, right? And what's that going to be? The expected value of x minus y squared. Now think about this. This will be the same, right? But what happens? In here, this is x minus y squared. Do you all follow me, class? So this is going to be, this part stays the same, or it's sigma z, which is going to be 7. Then it's going to be plus x bar minus y bar squared, or 0 squared. So that should just be, well, let me do it this way so you can see it over here. I'll do it this way one more time. The expected value of x minus y squared is the expected value of x squared plus the expected value of y squared. And then what we're going to get is minus the expected value, minus 2 times the expected value of xy. That's what I'm trying to say there. You all with me? And again, I'm trying to, if you just square that out, that's what you get. Do you all agree with this, class? Now, I'm going to write this down. So this expected value of x minus y squared, right here, expected value of x squared is sigma x squared plus x bar squared. I hope you agree. Expected value of y squared is plus sigma y squared plus y bar squared. Agree? Now that's minus instead of plus, so it's minus 2 times the expected value of xy. Do you agree with that? I know some of this is new, and I'm not trying to fly, but I'm trying to get one more thing done before the end of the class. With me? So what's this going to be? Well, minus 2 times the expected value of xy. Minus 2, the expected value of xy is what? Is sigma x, sigma y times the correlation coefficient, right? Plus the mean value of x, mean value of y. If you look at the that right there. Agreed? We need the expected value of xy, so rho sigma x, sigma y plus x bar, y bar, right? Now put in the values. So sigma x is 1 plus x bar is 1 squared is 1 plus sigma y squared is going to be 4 plus y bar squared is 1, right? Y bar. And then what do you get? Minus 2 times sigma x. Sigma x is 1, sigma y is 2, right? And, well, I'll do it this way. Minus 2 times, let me do it this way. All right, here I have sigma x is 1, sigma y is 2, and rho is 1/2, so that's 1, plus x bar is 1, y bar is 1 is plus 1. Do you agree with this, class, so far? So that's 4, minus 4, and 4, they cancel, it's 3. Do you agree with me, everyone? His answers are wrong in the book. Just do it methodically. Take the exact formula, plug in the values, and you'll find those answers are wrong. And I don't have an errata sheet available. I'll look for it. I want to do the next exercise. It's telling. The problems in the book actually are probably easy. Well, there's one that's not as easy, but most of them are very simple, and you have the solutions. Let's do the next exercise here. If you don't mind, this is, what, 3.2,
Dash 4.2.
but it is an exercise. Go ahead.
X is a zero mean random variable having a variance of 9, and
Sigma x squared
yeah.
equal 9. Go ahead.
y is another zero mean random variable.
Sigma y is unknown. The variance is unknown. Okay, go ahead.
The sum of x and y has a variance of 29, and the difference
Z
is a variance
equals
of 20,
x plus y. Go ahead. And this has a variance, right?
of 29,
X plus y squared is 29.
and the difference is a variance of 21.
They want to find sigma y. Isn't that right?
Find the variance of y.
Okay, now, they didn't give a correlation coefficient, did they? All right, we have going to have two equations, two unknown. I'm going to just put it up there. And I know remember, this is what we're going to go to with, all right? First part is a sum, so it's sigma x squared plus sigma y squared plus that. You all follow me? So come over here, I'm just going to fill in what we know. Over here, it's a sum. Sigma x is given as 9, right? I'm right here. Sigma y is unknown. Right? And then it's going to be plus, because it's a sum, plus it's 2 times a correlation coefficient times sigma x, which is going to be 3. If this is 9, that means sigma x is 3. And then it's times sigma y. That's the first equation. Now I'm taking that, and it's a sum, correct? So I'm using the positive in front of the 2 row. Now, the difference of the two here, and this is sigma squared of x minus y, is going to be equal to, and again, if it's a difference, it's the negative. Still sigma x, sigma y. Do you agree with me, class? So it's going to be 9 plus sigma y squared, and then it's going to be minus, I might as well just put down 6 rows sigma y. I'm going to put a 6 there too. There are two equations, two unknowns, and this is 21, right? I should put down this. Does everybody agree with me here? All right, how do you want to solve it? Personally, I look at this, I'm going to subtract this from that. I mean, you don't have to, but if I subtract this from this, I get 8, right? And then the 9's cancel, sigma y squareds cancel, and I get equal to 12 rho sigma y. Or I can say that rho is equal to, and if that's 12, that's what? 2/3, so it's going to be 2/3 divided by sigma y. Y'all agree with that? I just subtracted the 2. Now I'm going to take that and plug it into one or the other. It doesn't matter which one. We might as well do this one here. So now I get 21, I'm right here, is equal to 9 plus sigma y squared minus 6 times rho, and rho is 2/3 over sigma y times sigma y. Obviously, sigma y's cancel right there. Correct, class? Can you all see what I'm doing? What does this mean? Well, now I have 21 equal to 9 plus sigma y squared, and this is going to be minus what? Well, it's 6 divided by 3 is 2 minus 2 is 4. So I have this equation. Take everything to the other side. Well, 9 minus 4 is 5, correct? And take it to the other side. 21 minus 5 is 16 is equal to sigma y squared, or sigma y equals 4. You all agree with that? What else does he ask for in there?
Find the correlation coefficient of x and y.
All right, what's the correlation coefficient going to be? Isn't that it right there? So what is it going to be? That's 2 over 3 sigma y is 4. So that's 1/6, right? Agreed? The last part's the important one you see. All right. How many see what I'm doing up to this point? I'm moving a little quickly, but you all with me on this? It's just methodically using these equations, just applying them. There's no tricky magic or anything like that. Last one's a little tricky, and I want to do this part. Let me erase this part of the board first. I suppose there's a lot better ways to go about this, but I like to just state what it is explicitly and then go through and find a way to use what I know and get the information. Now he says a new variable equal to...
He says find the variance of u equals 3x minus 5y.
U equals what?
3x minus 5y.
All right, now he wants the variance of that. So he wants sigma squared of 3x minus 5y. Do you all follow me? Okay. So what I'm going to do is say this variance here I can get if I can get the expected value of u squared. So I'm going to get the expected value of, and here it's going to be 3x minus 5y squared. And I know what that's going to be is going to be the mean value squared of 3x bar minus 5y bar squared plus sigma squared of 3x plus, or minus 5y. Now the only thing I'm doing here is saying it doesn't matter what this is. Could be z, x, doesn't matter. But it's equal to the mean value of that, whatever it is, plus the variance, whatever it is. That's the only thing I'm saying. Correct, class? You all follow me, the reasoning behind it? Don't get hung up about that 3 and 5 business. So back to this. Remember, they want this. That's what they want. I'm sorry, they want this. This is what they want. We're going to get all that in a second. So if you look at this right here, that's the expected value of what? Well, 9x squared, right? Plus the expected value of 25y squared, right? And then it's going to be minus 30xy. Do you all agree with that?
X bar squared and y
30.
bar squared.
30 minus 30x times y. I'm just squaring out that. What?
I meant x bar squared and y bar squared. 9 times x bar squared.
No, it ain't. That's not an average value yet. This is the expected value of x and
shoot.
y.
Sorry.
This is over here.
I see. I thought I got confused.
You all with me? These are actual variables. Now, if you take a look at this, this is equal to the expected value here, or 9, sorry. 9 times the expected value of x squared would be sigma x squared plus x bar squared. I'm replacing these expected value of y squared now with sigma y squared plus y bar squared, so it's going to be plus 25. And now it's going to be equal to sigma y squared plus y bar squared. I'm just replacing this. Now when I take the expected value to last, it's minus 30 times the expected value of xy. And that's the expected value of this. Correct, class? I hope you all see this, right? Now listen, we got sigma x, we got x bar, we got sigma y, y bar. What is y bar and x bar before I go on? What were the average values for x and y?
The mean random variable, 0.
Right? Thank God. Let everybody say hallelujah. So the eraser works, right? Now, I'm going to rewrite it here just so you all see this. So it's going to be 9. What's sigma x squared?
Sigma x squared
9.
is 9.
Right? So it's 9 times 9 plus 25. What's y? We just want 16, isn't it? Y squared is 16. 25 times 16. This is going to be a whale of a number. Minus 30. And what is this expected value of xy? Rho, which we got, right? Rho times sigma x, sigma y, right? I'll write it down. Rho times sigma x, sigma y, plus x bar, y bar, right? Isn't that right? What are x bar? What's x bar? Ta-da! 0 to the rescue. So what's this? Now you're going to have to help me with this one. I can get the 81, I think, plus 25 times 16, whatever that may be. I don't feel like doing it. Minus 30 times, what was the correlation coefficient?
160.
All right, this is 16 here, so it's 25 times 16 minus, and this is 1/6. Sigma x was 9, or is 3, sorry, 3 and 4, right? 3 or 4 and 3, whatever. Now what is that? Because honestly, I didn't crunch the number on this one. I think it's right though. I should have. It's a big number, 4 something, 400 and whatever. But just do the math. What did you get?
421.
Is that what he has?
Yes, sir, he does.
421. But you all follow me on this? Now next time I'm going to talk about how you can actually, anytime you have this kind of a thing, we're going to find out there's a reduction formula for that, and I'll talk about it. It's going to be that coefficient squared times sigma x squared plus sigma y squared, that coefficient squared plus y bar squared plus sigma y squared, and then what you're going to do is take twice the product of that with a minus sign or a plus times rho expected value of, basically I replaced the expected value of xy with sigma x, sigma y times rho plus mean value of x, mean value of y. He was nice to make them both 0. I'm going to give you the homework. Please do the homework for Wednesday. I was trying to get through these exercises and go through the theory. Some of that theory, by the way he puts it out there in a book, I was looking through that, I'm thinking you can miss it with all that normalization. Okay, any questions? Controlled madness. That sounds like our class. All right, see you on Wednesday. Did everybody understand this at least? Got a grasp? The homework will bring it out. Please try to do the homework as soon as you can. You'll be thankful you do, because the next thing gets really a little hairy. The next thing it's like the wine problem. Remember that? The first time through that, it was like, huh? Then after well, if you don't keep up with this next section is really going to get a little crazy. And it has to do, when we get into some stuff, when we get two density functions, we actually get Fourier transforms or Laplace transform stuff. They call it a characteristic function, but it's just a Laplace or Fourier transform. Remember how convolution in one domain was actually equal to multiplication in the other in frequency domain? Here, you're going to see the correlation, which is really almost the same as convolution, except with convolution, you remember if you convolve f of x and times g of x, you get an integral of f of lambda and then g of, and it's going to be like or x minus lambda d lambda. There's a minus there, right? With correlation, it's a plus. Same, but the neat thing is, I hated convolution. There was some, but if you take it into the frequency domain, it's simple multiplication. You weren't even needed this time.
Now it's just exercises. That's all the end of the chapters.
You said like on one of the exercises the stuff was wrong. Have you worked through the problems to see if he's gotten errors?
I didn't do them. I don't think I did all. Well, wait, I did some of the problems in this section. I haven't found an error in the problems.
Mm-hmm.
If I do, I'll let you know. I'll do them all by next time. I looked through a bunch and did them. If there's an error, I'll let you know. But generally speaking, you can tell when there's an error. If he has 3 plus 3 is 12, that's a dead giveaway.